So in the previous lecture, we started talking about methods of determination of surface and interfacial tension. We have seen the very first and simple method, that was capillary rise method. Let us talk about the second method, which is used for determination of surface as well as interfacial tension. It is a drop formation method, and it is commonly used in the laboratories for determination of surface and interfacial tension because of its simplicity, and the apparatus which is required for determination using this method is a very simple and cheaper one. As we know that a drop of liquid is allowed to form at the lower end of a capillary tube. Even you must have seen when we close the tap, loosely close the tap, at that time, most of the time, you have one drop of a liquid which is hanging at the aperture. And that drop keeps hanging till the downward force is not equal to the upward force which is leading that drop to be hanging from the surface of the aperture. So in this method also, we are trying to understand how this surface tension of a liquid, which acts as upward force, keeping that drop hanging from the aperture, it drops down only when the weight of the liquid exceeds. So the drop is being supported by the upward force of a surface tension acting at the circumference of the tube. The weight of the drop, that is mg, mass into gravitational force, it pulls it downward. When these two forces are balanced, the drop breaks and it falls down. Now, being this upward force is a function of a surface tension, we can determine it with the help of the weight of the drop, and there are two ways by which it is being done. The equation which we can get at the point of breaking is your upward force becomes equal or is at equilibrium with the downward force. Upward force is your 2 pi r surface tension and downward force is your weight of the drop. So we get mg is equal to 2 pi r gamma. M is nothing but it is the mass of the drop. G is acceleration due to gravity. And when it becomes equal to the circumference of the capillary from which it is coming out and the surface tension of that liquid. Here in this equation, M is denoting the mass of the drop, G is acceleration due to gravity, and R is the radius of the tube. The apparatus which is employed for determination of surface and interfacial tension using drop formation method is a glass pipette with a capillary at the lower part. This glass apparatus is called as stalagmometer or simply a drop pipette. It is cleaned, dried and filled with the experimental liquid, say up to mark A, and then the surface tension is determined by one of the two methods. One method is known as drop weight method and second method is known as drop count method. We have used both these methods into the lab for determination of surface as well as interfacial tension. So let us discuss both these methods which works onto the principle of drop formation method. One is drop weight method and another one is drop count method. In both the techniques, stalagmometer is the glass apparatus which is being used. It is required to be thoroughly cleaned and dried before starting the experiment. or filling up with the experimental liquid. Say the experimental liquid is being filled up to the mark A. Then about 20 drops of the given liquid are received from the drop pipette in weighing bottle, and it is being weighed. When we know the weight of 20 drops, obviously and easily we can determine the weight of one drop. Then the drop pipette or that stalagmometer is again cleaned and dried, and now it is being filled with the second liquid which we are using as a reference liquid, say for example water, and same procedure is being carried out for that liquid as well. 20 drops of the reference liquid are being received into the weighing bottle, and it is weighed, and the weight of one drop is being determined. Now we know the equation that mg is equal to 2 pi r gamma. That was our equation number 1. From that equation, we can use it for liquid which is under investigation and liquid which is a reference one, say water. So for experimental liquid, it is m1g is equal to 2 pi r gamma 1. That is mass of the 20 drops of the liquid, experimental liquid. Acceleration due to gravity is equal to 2 pi r. Gamma 1 is the surface tension which we are interested in determining. M2g is mass of the reference liquid into acceleration due to gravity, and gamma 2 is nothing but it is the surface tension of the reference liquid which is being known to us. Now 2 pi r will get nullified because we are using the same drop pipette. Now in this particular experiment we have to be careful that we are using the same drop pipette or stalagmometer which we have used for the experimental liquid. Same drop pipette needs to be used for experimental as well as reference liquid. Then and then only the 2 pi r, this factor will be nullified. If we change the stalagmometer, there can be variation into the radius of the pipette, radius of the capillary tube which is there in that drop pipette or stalagmometer, and that will lead to the errors into the results. So we came up with the equation. When we divide equation 2 by equation number 3, we get gamma 1 by gamma 2 is equal to m1 by m2. So surface tension of experimental liquid divided by surface tension of a reference liquid will be equal to the weight of the drops of reference liquid, test liquid or experimental liquid divided by weight of the drops of the reference liquid. So knowing the surface tension of the reference liquid from the table, we can determine the surface tension of investigation liquid or experimental liquid. This is the simple drop weight method which we have used into the lab. Is it clear? So this is your drop weight method. Next is drop number method. The same stalagmometer or drop pipette is being used for this particular method as well. The drop pipette is first filled up to the mark A with experimental liquid, and the number of drops is counted as the meniscus travels from mark A to mark B. Now you have noted down the number of drops of the experimental liquid which are formed when it runs from mark A to mark B. Clean the pipette, clean that stalagmometer, dry it, and fill it with the reference liquid. say for example water, and allow the number of drops to be formed when the meniscus passes from mark A to mark B. Note it down. So you have got the number of drops of the reference liquid from mark A to mark B. You have got the number of drops of the experimental liquid when it runs from mark A to mark B. Let N1 and N2 be the number of drops which are produced by the same volume of the two liquids. As you are allowing these two liquids to pass from mark A to mark B, which is constant, so the volume of both the liquids is same. What will change will be the number of drops which will be formed, and why it will change is because of the difference in their surface tension. So this is important, and because of this only, again you have to remember that same stalagmometer is to be used for counting the number of drops of reference as well as experimental liquid, because the bulb across which you are going to count the number of drops, it will vary from one stalagmometer to another one, and it will lead to the changes into the volume of both the liquids. To have volume of both the liquids remaining constant, because this particular factor is going to be nullified from the equation, so we have to ensure that we use the same stalagmometer for counting the number of drops of experimental as well as reference liquid. Now we can determine the volume of one drop of liquid, volume divided by N1, means whatever volume of the liquid was there which has run from mark A to mark B, divided by the number of drops which are formed. That will give you the volume of one drop of liquid. And now when we want to convert this number of drops into the mass of one drop, we will have to multiply this volume by density, because we know that density is nothing but it is mass upon volume. So if we want to determine the mass, it will be simple: volume of one drop of liquid into density, where D1 is the density of liquid 1. Now same thing will be done for another liquid, or say reference liquid. N1 is the number of drops of the experimental liquid. N2, consider it as the number of drops of the reference liquid. We have determined the mass of one drop of liquid, which is experimental liquid, whose surface tension we are interested in determining. So similarly, the mass of one drop of liquid 2, which is reference liquid, will become equal to V by N2 into D2. Then from equation 4, we have got equation into drop weight method, that was gamma 1 by gamma 2 is equal to M1 by M2. Now we have got the values of M1 and M2. M1 is mass of one drop of experimental liquid. M2 is mass of one drop of a reference liquid. Putting these values into the equation, we get gamma 1 by gamma 2 is equal to V is the volume of the liquid divided by N1, that is number of drops which so here we put the values of M1 and M2 into the equation, that is gamma 1 by gamma 2 is equal to V upon N1 into D1 divided by V upon N2 into D2, where V remains constant and it will be nullified because we have kept the same stalagmometer. So the volume of either reference liquid or experimental liquid which is running or traveling from mark A to mark B, it will remain constant, and it will be nullified because volume of both the liquids will remain same. What varies is the number of drops which are being formed, and it varies because of the difference into the surface tension we already spoken about. So when this equation is being simplified, we get gamma 1 by gamma 2, that is surface tension of experimental liquid which we are interested in determining, divided by surface tension of a reference liquid, will be equal to N2 into D1. N2 is nothing but it is the number of drops which are formed of a reference liquid when that liquid runs from mark A to mark B, into D1. D1 is nothing but it is the density of the experimental liquid, divided by N1 into D2. N1 is nothing but it is the number of drops of experimental liquid that are formed when it runs from mark A to mark B, and D2 is nothing but it is the density of the reference liquid. Most of the times, reference liquid which is being used for determination of surface and interfacial tension is water. And for water, these values of surface tension at different temperature are being documented. So you can take the values of surface tension according to the room temperature, put it into the equation, determine the density of reference as well as experimental liquid, and count the number of drops of reference as well as experimental liquid. Put the values into the equation and you can directly calculate the surface tension. So the values of D1 and D2, that is densities of experimental liquid and reference liquid, it is being determined with the help of picnometer or density bottle, and knowing the value of surface tension of reference liquid, which is mostly water, from the table at that particular temperature, we can easily determine or calculate the surface tension of experimental liquid. Same procedure, same thing is being used for determination of interfacial tension as well. In case of surface tension, we allow the drops to be formed in air, and in case of interfacial tension, we allow two immiscible liquid to form drop. One liquid will be taken into the beaker, another liquid which is immiscible will be taken into the stalagmometer. The lower end of the stalagmometer will be dipped into the liquid which is taken into the beaker, and will allow the liquid which is there into the stalagmometer to start forming a drop when the lower end of the stalagmometer touches the liquid into the beaker, and will allow the liquid into the stalagmometer to run from mark A to mark B. We'll reverse the process. The liquid which is there into the stalagmometer will be taken into the beaker now, and the liquid which was there into the beaker will be taken into stalagmometer, allowing the liquid into the stalagmometer to form drops when the lower end of the stalagmometer is in touch or it is being immersed into the liquid which is there into the beaker. Knowing the number of drops which are formed when liquid runs from mark A to mark B for liquid 1 and for liquid 2, we'll put the values into the equation to determine the interfacial tension. In that case, the interfacial tension will be given by later gamma LL. Gamma LL stands for interfacial tension of one liquid against another liquid. Procedure remains simple and same as we have used it for surface tension. In case of surface tension, drops are allowed to be formed in water. In case of interfacial tension, one liquid is forming drop when it is in contact with another immiscible liquid. Next, we'll start talking about the third method of determination of surface and interfacial tension, that is your Bunoy ring tensiometer or ring detachment method. Thank you.